refrigeration systems form an integral part of industries where products need to be rapidly cooled or protected under cool temperature. The basic components of a refrigeration cycle include compressor, condenser, evaporator, and expansion valve. A condenser is a heat exchanger used to condense the working fluid or refrigerant after it's been heated up during the compressor process. The product needs to be cooled rapidly in order to preserve it. Most units therefore have massive refrigeration systems, and accompanying these systems are condensers that cool the coolant. Conventionally, technologies such as plate heat exchanger and shell and tube heat exchangers are used to condense the refrigerant to liquid. Both technologies have their drawbacks. Shell and tube exchangers are less efficient when compared to plate heat exchangers. Plate heat exchangers require high pressure to operate and consume high amounts of energy. An energy-efficient alternative is the evaporative condenser. The condenser is a metal box with a water tank at the bottom, a water pump, condenser coils which carry the coolant sprayers, and fans which blow air onto the condensing coils. The coils may or may not be finned. The process begins with the water pump moving cool water to the sprayers at the top of the condenser. The vapor to be condensed is circulated through a condensing coil, which is continually wetted on the outside by a recirculating water system. Air is pulled over the coil, causing a small portion of the recirculating water to evaporate. The evaporation removes heat from the vapor in the coil, causing it to condense. The heat exchanger effectiveness can be calculated using the formula effectiveness equals actual heat transfer divided by maximum possible heat transfer. Compared to conventional technologies, evaporative condensers have several advantages such as heat rejection in an evaporative condenser takes place in a single unit, which results in maximum efficiency. Evaporative condensers can offer operating and maintenance savings by as much as 20%. Evaporative condenser requires relatively smaller area for installation. To understand the cost-benefit analysis, let us consider an evaporative condenser of 200 TR capacity. The installation can lead to a saving of around 1,30,000 rupees annually compared to cooling tower-based condenser system. This implies an energy saving of 10 to 15 tons of oil equivalent of energy, monetary savings of 6 to 8 lakh rupees, and GHG emission reduction of 110 to 130 tons of carbon dioxide emissions per year. The installation will require an investment of 12 to 15 lakh rupees, which can be recovered within 2 years.
Major benefits of this condenser is, first of all, we look for this energy efficiency. Secondly, in case of water usage, 40% water is less consumption in this case. And third one is the most important, which is condensing temperature is maintained 38 to 37 degree, which is saving major power saving in compressor motor.
Evaporative condenser is best suited for hot and dry region. A condenser should be selected based on climatic conditions. One of the important parameters to ensure optimum efficiency in an evaporative condenser is to select the correct capacity of the equipment. Also, regular preventive maintenance allows maintaining optimum efficiency. Performance of evaporative condensers is affected in humid atmospheres. Evaporative condensers are a cost-effective and energy-efficient solution for the conventional shell and tube and plate heat exchanger. The technology, if implemented in 100 units of average 200 TR capacity each, will lead to a saving of 1,000 tons of oil equivalent of energy and 11,000 tons of carbon dioxide emissions annually.